Dude, side. More. 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 Okay, go back the other way. Do forward and back. Go the other way.
Hey Google, what's the weather today?
Today in Toronto, it'll be rainy with a forecasted high of 52 and a low of 42.
Displayed here is the process of designing the body parts of the cat, which was created entirely from scratch. The measurements were taken with great precision, and the designs were created using Fusion 360 to produce accurate geometries. Finally, the designs were brought to life through 3D printing, which added layer upon layer to create the robotic cat. Displayed here is the block diagram that illustrates the connection between all the components of the cat. First off, we have a power delivery system that consists of 2 lithium-ion batteries. Each powers a 5V and a 6V DC to DC converter, which is displayed as the bulk converter shown in the diagram to step down the voltage. The 5V converter, it basically powers the Raspberry Pi, which then in turn powers the Arduino via USB. The 6V converter powers the PCA board, as it can be seen. Also, the servos are all connected to the PCA board, which are then all connected to the Arduino, so that when movements are requested, specific signals are sent to control the necessary servos to see the cat behave in the requested way. As it can be seen, the system also includes a gyroscope connected to the Arduino for the self-stabilization feature as shown earlier. It also has the ultrasonic sensor to detect and avoid obstacles. This is basically done by emitting high frequency sound waves and measuring the time it takes to bounce back. And that information is used to help the cat avoid obstacles, detect and avoid obstacles. As it can also be seen on the right, the servos used for the tail and head, it states that we use the SG90 servos. However, there's an updated block diagram, and instead of the SG90 servos for the head and tail, we use the MG92B servos due to their metallic nature and greater torque, which was very necessary for the fall recovery feature as shown earlier in the video. In terms of the peripherals, the Raspberry Pi, it has a micro SD card that has the appropriate operating system installed on it for the project. Additionally, it also has a speaker and a microphone connected to it to allow for the Google Assistant interaction that was shown earlier in the video. So this is the block diagram showing how everything was being controlled. So we essentially had 2 stages. We had the upper stage and the lower stage to control the cat. The upper stage control was carried out through the Raspberry Pi, while the lower stage was carried out through the Arduino. So for the upper stage, what happens was the Raspberry Pi communicates with the Arduino to perform actions through a Python script executed in Thonny. So basically, once the Raspberry Pi is connected to a wireless network, we access the Raspberry Pi desktop through a VNC connection, where we can open a Python script in Thonny, run it, then execute the desired movement that we want to see. The desired movement what is associated to a function that's already programmed on the Arduino. So every time we enter a movement, it calls the associated function on the Arduino, which then moves the servos in the programmed combination to produce the movement that was called for. In terms of the lower stage, so as mentioned, it uses the Arduino. The Arduino is used to communicate with all the servos and the two sensors. The purpose of the Arduino is to control the angle of the servos to achieve the requested movements like walking, turning, posing, etc. For the ultrasonic sensor, it basically detects information which is read by the Arduino to detect and avoid obstacles. Also, for the gyroscope sensor, the Arduino, it performs basic movements to control, such as adjusting the leg poses by the data received from the gyroscope to achieve the self-balancing feature.